Hello, today's video is about calculating average values. So I'm just going to work through a few problems on my iPad here. So the first problem that we have is find the average value of the function f of x equals 1 over x on the interval from 1 to 4. So you can see here on the iPad, we have marked out already the interval starting at 1, running out to 4. And you can also see that we've already put in an average value line, which makes the red rectangle. And you can see that the area of the red rectangle looks to be about the area under the curve. So if we were to take the area that's over here under the curve and sort of dump it in to the right, the area that we have to the left here would match the area that is to the right. In fact, I coded this into MATLAB, so the red line is in fact the average value of f of x, or on the interval from 1 to 4. So it matches up very nicely. So what we want to do is figure that out, what that value is, using calculus. So like we had said in the previous video, we know that the average height of the red box times its width, which would be b minus a, must be equal to the integral of the blue under the blue curve, which would be the integral from a to b of f of x dx. And so then to find the average value, we just need to take the integral from a to b of f of x dx and put that over the denominator b minus a. So continuing on, in this specific case, what that looks like is the following. We need to take, in order to find the average value, we need the integral starting at x equals 1 up until x equals 4 of the function 1 over x integrated with respect to x all over 4 minus 1. Now, when you look at this, this is one that's on the memory list when we go to integrate. So we know that the antiderivative of 1 over x is in fact ln of x with absolute value signs around it. So we know that this should equal the natural log of the absolute value of x evaluated at 1 and 4. And we can put that over a denominator of 3. Let's get rid of that. And we don't need the absolute value sign since all of the numbers are positive. And we know that ln, let's switch colors here, ln of 1, we know that that is in fact 0. So we can rewrite this as the natural log of 4 over 3. And if we evaluate that on a calculator, we can see that its decimal value is 0.462, which works out nicely because if we go back to the graph and extend the average value line over, it's in that region right there. It looks like it's a little less than 0.5, so 0.462 works out pretty nicely. Now here we have a second problem. This one's going to be a little bit trickier, but let's see what happens here. So we need to find the average value of the function x times the cosine of the quantity x squared on the integral from 0 to the square root of pi. And you can see that is graphed out here in MATLAB. And you can see there's something interesting here. It looks like the average is going to be 0. So if we look at this, the average height line is right on the x-axis, because if we take the area that's above the average value line in the left part of this, and we were to sort of pour it over into the right part, it looks like this area here actually could fill that in pretty nicely. So we know that it's at least close to 0. So let's prove that it actually is 0. So once again, we can go to our formula that we know that the average value is equal to the integral in this case from 0 to the square root of pi of x times the cosine of x squared with respect to x, all over the square root of pi minus 0. So that's just filling in the average value formula. And so now we want to look at this and see if we can figure out what to do with this integrand. Okay? So when we look at that, it's clearly not on the memory list. So we should always ask ourselves, is it, if we go back to here, whoops, is it on the memory list? The answer to this is no. Can we do algebra to make it match the memory list? And in this case, the answer is no. Multiplying, we can't multiply the x times the cosine of x squared and get anywhere. So that's not helpful. So the next choice is substitution. And that will work very nicely in this problem. So let's just rewrite the integral down here and figure out what the numerator will be. So we have the integral from 0 to the square root of pi of x times the cosine of x squared dx. And we need to figure out what to substitute for. So it's a little bit of quick guessing. If we substitute for x, that doesn't really get us anywhere because its derivative is 1. So the next most complicated thing to substitute for would be x squared. If we were to substitute or take its derivative, that would be 2x, which is pretty nice because that's close to, we have an x as a factor. And so 2x is a pretty close match to that. So let me do that substitution. Let's let u equal x squared. So if we continue onward, then we know du dx is 2x, and then you can say du is equal to 2x dx. And then if you wish, there are a couple ways to do this. We can see that if we were to put a 1/2 in front of the integral, we would have a 2x. We could put a 2x inside of the integral, and we would have a 2x dx right there. And we have the cosine of x squared as the other part of that. So we can rewrite this whole thing as 1/2 the integral of, we need to be careful, let's not put our limits on yet, but we can just put in cosine of u du. So just a quick reminder, okay, du is the 2x dx part, and x squared is u. So we can say that this is equal to the cosine of u du. Now let's take care of the limits here. Let's make a little limit table. When for x and u, when x is 0, u is equal to x squared, so that is also 0. When x is the square root of pi, u should be pi. So the limits for the new integral go from 0 to pi. Now, if we look at what we have, cosine of u would be on the memory list. So we can turn around and rewrite the integral that we have here as 1/2. The antiderivative of cosine u is sine of u. Evaluate it at 0 and pi. So then we would take 1/2 and we would put the sine of pi minus the sine of 0 in. And we should know that both of those are zeros. So both of those go to 0. So the answer is, in fact, 0. So that matches what we were expecting. Let's move on to problem 3. So in example 3, we're supposed to find the average value of the function e raised to the negative x squared. So once again, we could start with f of x is equal to the area under the curve. So that would be the integral from 0 to 2 of e to the negative x squared dx all over the width of the interval from 2 to 0. So that's a width of 2 minus 0. So we take the area and divide by the width. We will, in fact, not get f of x. Let me get rid of that. We will get the average value of x. So that should give us the average value of x. We can see, looking at the picture created on MATLAB, that the average value is right here. That looks to be just a little bit more than 0.4, maybe around 0.45 or 0.425. So we're expecting to be about, let's just say 4.4 as an answer. So let's go through and try to evaluate this. Okay, so first of all, we should ask, is this on the memory list? And the answer is no. Can we do algebra to evaluate the numerator, that is? And the answer is no. Can we do substitution? There are a couple possibilities of things that we could sub for. We could let probably u equal negative x squared would be a good guess. But if you take the derivative of that, you would get a negative 2x. And there is not a factor of negative 2x anywhere to be seen. So this just doesn't work. So that is also a no. Turns out the integral of e to the negative x squared is something that we simply cannot get an exact value for. So the best that we can do is actually just get out our calculator and use the integral function and look under math and go all the way down to fn int, or on some calculators it will actually have an integral sign. So look that up, and after you do that, just put in the integral from 0 to 2 of e to the negative x squared dx, and your calculator, when you do that, should give you a value of about 0.882. So when you divide that by 2, then we should get that f average is equal to 0.882 over 2, which is 0.441, which is extremely close to the guess. Remember, we were expecting about 4.4. So our answer of 0.441 is extremely close to the expected value. Now I'm just going to take a moment to show you how you could have found this using MATLAB. So let me pause the video for just a moment. So now you can see my MATLAB screen. So let me look in the command window here. So let me make the command window nice and large. Let me clear the command window, and let's figure out how we would figure out where the average value line is using MATLAB. So as we said, we need to find the integral from 0 to 2 of the function. So first of all, we need to declare variables. So we have to tell MATLAB that x is our symbolic variable, and we need to put in, we need to define what the function is. So one way to do that is to say y equals, remember e2 something is exp in MATLAB for exponential, negative x squared. We don't put in the dot now because we're not working with a vector of x values, we're working symbolically with x. And if we keep on going, now that we've defined y, we can simply integrate. Let's actually make this, I'm going to call this the area, is int of y, so that'll take the function that we have stored as y, with respect to x from 0 to 2. So if we put that in, it tells us that the area is this complicated function. You probably don't know what the ERF2 function is. So because we don't know that, let's actually change it to a number. So we're going to take the area and we're going to assign it the numerically evaluated value for the area. So we can see that the area is 0.8821. Now that's the area under the blue curve. We now still need to figure out what the average value is. So to find the average value, we could just say AVG is equal to the area divided by, remember it's B minus A, which was just 2 minus 0. And if we put that in, we end up with 0.441. And if we go up to our graph here, we can see that that's a really good approximation. In fact, if we zoom in on the average value line, we can see where that is. It's right up there, very, very close to what we just got in MATLAB. In fact, it's exactly where we just calculated in MATLAB. Let me stop the video now.